welcome back to the channel. So today in this video lecture we're going to be solving this problem, shortest cycle in a graph. So in this problem we're given a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1, and there is a 2D integer array, like it contains a pair of numbers, pairs of integers, where each pair represents an edge between the two nodes. Every vertex pair is connected by at most one edge. That means there are no multiple edges. Also, there are no self edges. What we have to do in this problem is to return the length of the shortest cycle in the graph. If there is no such cycle, if no cycle exists, then we return -1. Okay, so what is a cycle? A cycle is basically a path that starts and ends at the same node, and each edge in the path is used only once. Okay, so let's better understand the problem statement using an example. So here we have a graph. This graph contains 7 vertices. They are numbered from 0 to 6, and we want to find the length of the shortest cycle in this graph. So what is the strategy to solve this problem? Before that, what will be the shortest cycle in this particular graph? We can see that the shortest cycle is this, that is this one, which starts at node 0 and ends at node 0, like moving from 0 to 2, then from 2 to 1, and finally from 1 to 0. So the cycle which starts at node number 0, 2 or 1 is the shortest cycle, and it has a length of 3 because it contains 3 edges. Okay, there's also another cycle we can see here which starts at node 3, 6, 5 or 4. It has a length of 4 because it has 4 edges, but this is more optimal answer, hence the answer for this test case is 3. Fine. So how can I solve this problem? What is the strategy to solve this problem? We know how can I detect a cycle using breadth first search. We know the strategy to detect the cycle or to find the length of a cycle using BFS strategy. That is, let's say I want to find the length of the cycle which starts at node number 0. So what I will do is I will perform a BFS from node number 0. So take a queue, push 0 into this queue. Also we have to keep track of the parent. Why? So that we do not visit the same vertex or the parent vertex again while traversing the adjacent nodes. Like initially I have 0 in the queue. Now I pop this 0 out of the queue, and the parent for node number 0 will be -1 because this is the starting node. Now this is out, traverse the adjacent nodes, that will be node number 2 and node number 1. So push these nodes, push node number 2, push node number 1 into the priority queue. And also for node number 2 and node number 1, the parent will be 0 now. Okay, the parent will be 0. Now again pop node number 2 here. So from node number 2 I can move to node number 1 and node number 0. Okay, these are the nodes where I can move. But here I see that node number 0 is basically the parent node, while node number 1 is already visited. Now we encounter an already visited node. That means there is a cycle. Fine, because we can see that this is the parent node and this node, which is 1, is already visited. So in this case what I will do, I will simply find the distance from the source node, which is 0, till this node 2, that will be 1, and the distance from the source node 0 to this node 1, which will be 1 again, and we also connect this edge in this cycle, and that will add one more 1 in this answer, giving me a final answer of 3. So in this fashion I detect a cycle. So how can I use this strategy to solve my problem? It's simple. All we have to do is to just perform BFS from every vertex of the graph. So start from vertex number 0, go until vertex number n minus 1, take every vertex and perform BFS strategy to detect the cycle. And for every time whenever you find a cycle in the graph, simply update the length of the cycle which we have calculated till now. So for that, basically initialize a variable, let's call it answer, initialize it with a very large number, let's call it int max, okay, because this will store my final cycle length, okay. So store very large number in this answer variable. Now perform BFS from every node starting from 0 till n minus 1, and for every node if there is a cycle, then simply update this answer variable with the length of that cycle. So if I find a cycle with a lesser length, then this answer will be updated. Finally, at the end of the iteration, I will have the shortest length of the cycle which is present in the given graph. Fine. So that's all we have to do in this problem. It's a pretty simple problem if we follow the naive strategy, which is using BFS search from every vertex. And let's just jump to the code implementation part. So this is the find shortest cycle function. So let's declare an adjacency list to store the given graph. It will have n plus 1 nodes. So iterate over the edges and create this adjacency list. We have bidirectional graph. Okay, now also declare a global variable, let's call it answer, initialize it to a very large number. Now iterate over every vertex starting from vertex number 0 till n minus 1, and for every vertex declare a visited array, visited bool n plus 1, initialize it with false, and a vector or an array, let's call it, what do we call this vector? This is distance vector. Initialize it with the very large number, let's say 1e9. Now perform BFS from this current node, pass the adjacency list, the visited array, the distance array, and simply calculate the cycle length if there is a cycle. So at the end of all of this iteration, if the answer contains int max, that means there is no cycle in the graph, and in this case return -1, otherwise return answer. Okay, so let's say we have here BFS function. In this BFS function we have node, we have vector of we have adjacency list, then we have visited array, then we have a distance array. Okay, and here let's take a queue of pair, and push this node into this queue with its parent. So -1 is the parent for this node because we are starting from this particular node. We want to detect the cycle which starts at this node. Okay. Now iterate till this queue is not empty. Pop the top pair from the queue and its parent, which will be q dot front dot second. Okay, now iterate over the neighbor nodes of the current node. Okay, for the neighbor node, check if this is not visited. If it is not visited, then in this case simply update the distance for this neighbor node with distance of the parent plus 1 and push this node into the queue. Push it and its parent will be node. Otherwise, if it is visited, then that means check if this node is not the parent node. Okay, so we also have to keep track of the parent. Okay, we have parent here. If it is not the parent, in that case we are encountering a vertex, we are encountering a node which we already visited. That means there must be a cycle, and in this case we have to update our answer variable. So main of answer, it would be distance, so it's dis distance till this it plus distance till this node plus 1. Okay, so that's all. We also have to pop this node from here. Fine, so that's okay. We have distance it. Okay, so I think that's all. Let's mark it visited. We visit true, we visited true over here. Visit this vertex node and let's call it true, and the distance for this node where we are starting is 0. Okay, now whenever we are pushing a new node, we have to visit it, we have to mark it as visited, and that's all, I think. Let's see if it works. Oh, it's not it, it's it. It's is not equal to parent. Okay, okay, let's submit it. So that's all. So let's discuss the time and space complexity. We know we are iterating over all of the vertices, which takes in big of n time complexity, and for every iteration, for every node I'm iterating, I'm basically performing BFS, which has a time complexity of again big of n plus e, where n are the number of edges, e are the number of, like n are the number of nodes and e are the number of edges, giving me an overall time complexity of big of n square. Okay, while the space complexity is again big of n because I'm using a queue here. So let's see the constraints of this problem. We see that n goes up to 1000 only. That's why this algorithm worked here. Okay, big of n square worked for this problem because n is just like 1000, and 1000 into 1000 will give me 10 raised to the power 6, and it will work fine within the time constraints because we know that there are 10 raised to the power 8 iterations in 1 unit of time. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel and stay tuned with me for further updates on the channel, and I hope to see you all in my next video.